Solvent pop and boiling are among the most critical evaporation-driven defects in solvent-borne automotive coatings because they originate silently during film formation and only reveal themselves once damage is irreversible. From an OEM RD&I perspective, these defects are not random events, but predictable outcomes of solvent evaporation imbalance, skin formation, and internal pressure buildup within the coating film. Understanding them requires shifting focus from what happens on the surface to what happens inside the film thickness during flash-off and early bake. Visually, solvent pop appears as tiny pinholes or crater-like voids, often clustered, giving the surface a peppered or porous appearance. Under magnification, these defects show broken bubble structures or volcano-shaped openings where pressurized solvent vapor has ruptured the surface. In severe cases, the film may show widespread pitting or even collapsed craters after rupture. Boiling represents the extreme end of the same mechanism, where rapid solvent vaporization causes violent surface disruption, often visible immediately during bake ramp-up. The root mechanism begins with solvent entrapment. In any solvent-borne coating, evaporation occurs from the surface downward. As fast solvents leave the top layer, viscosity increases rapidly, forming a semi-gelled skin. If slower, high-boiling tail solvents remain trapped beneath the skin. They continue to absorb thermal energy during flash-off or oven ramp-up. As temperature rises, vapor pressure inside the film increases. Once this internal pressure exceeds the mechanical strength of the partially cured surface, the vapor escapes explosively, rupturing the film and creating solvent pop. Film build plays a decisive role because thicker films dramatically increase diffusion path length for solvents. As film thickness increases, the time required for tail solvents to migrate to the surface rises non-linearly. This is why solvent pop often appears only when DFT crosses a critical threshold, even if the same formulation sprays cleanly at lower builds. In OEM plants, this frequently occurs on horizontal surfaces, overlap zones, or repair areas where local film build unintentionally increases. Flash-off time is equally critical. Insufficient flash-off prevents proper evaporation of slower solvents before thermal input begins. Moving parts into the oven too quickly is one of the most common root causes of solvent pop, especially under production pressure. The defect may not appear immediately, but will manifest during bake ramp or shortly after full cure, making it particularly expensive to correct. Solvent balance is the most misunderstood contributor. Using a fast reducer in high-temperature environments is a classic mistake. Fast solvents evaporate too quickly, accelerating skin formation and sealing in slower components. This creates a high-risk condition where internal pressure builds rapidly during bake. In contrast, a properly balanced solvent blend with adequate mid and slow evaporating components keeps the film open longer, allowing continuous solvent diffusion and pressure release before skin strength becomes too high. Additives play a supporting but limited role. Defoamers and air release additives can help collapse entrained air bubbles introduced during mixing or application, but they cannot relieve solvent vapor pressure once skinning has occurred. Flow and leveling additives do not prevent solvent pop and should not be relied upon as corrective tools. In some cases, incorrect additive selection can worsen the problem by accelerating surface closure or reducing surface elasticity. Temperature management is often underestimated. High panel temperature entering the booth increases initial evaporation rate, while aggressive oven ramp profiles intensify internal vapor pressure before sufficient cross-linking occurs to strengthen the film uniformly. OEM best practice uses controlled ramp-up zones to allow residual solvents to escape gradually before reaching peak cure temperature. Viscosity also influences risk. Low viscosity coatings tend to spray at higher film builds and may encourage over-application. High viscosity systems may trap solvent more easily if atomization is poor, leading to localized thick regions. Therefore, viscosity must be controlled not just for application quality, but for solvent release behavior. Once solvent pop has occurred, there is no chemical fix. The only corrective action is mechanical removal of the damaged film, followed by repainting under corrected process conditions. Attempts to polish or bury solvent pop under additional layers only mask the defect temporarily and often lead to durability failures later. From an OEM troubleshooting standpoint, solvent pop must be approached systematically. First, verify actual film builds across the panel, not just target values. Second, audit real flash-off times under production conditions, not laboratory assumptions. Third, review solvent blend selection against booth and ambient temperature. Fourth, evaluate oven ramp profiles rather than peak metal temperature alone. Plants that control these variables eliminate solvent pop reliably without endless formulation changes. The key takeaway is that solvent pop is not a mystery defect. It is a pressure relief failure caused by poor solvent escape timing. Control solvent evaporation, keep the film open long enough, and manage thermal input correctly, and the defect disappears entirely. If you have questions about solvent pop, boiling, or unexplained pinholing appearing after bake, drop them in the comments. We'll break down real OEM plant cases and correction strategies in future episodes.